So welcome everyone. So this is the talk where you have the title right here, so you can see this in case you were like coming for a different track. So my name is Jakub Nabrdalik, and I'm a very boring guy. So basically, you got the link down there in case you are interested in what I do. But what I do is actually important from the perspective of this talk, because what I do right these days is actually I work at a company where I both implement and basically move large monolithic systems to the cloud for several customers or help them do it. I write microservices. Usually I found out that in the last 6 years, I wrote 30 of them. I designed the systems, and I both design the systems that I actually implement and keep alive for like 3 years. And also I design systems for other companies where they just ask me to help them out and basically help them design the system, or quite often to actually look at the architecture that they have before they go off to production or after they do, to verify what went wrong, basically, right? And also, on top of all of that, I do a lot of workshops, and I mean like really a lot of workshops, more than 100 right now, and those workshops are usually about things like reactive programming, but also architecture. And I see people making the same mistakes that I do. So basically, I wanted to give you that talk that will like keep you protected from when you're entering that scene, right? So basically, what I've learned during the years is that there is no such thing as a bad architecture. It's usually not because somebody is a bad architect. It's usually due to the bad education, lack of experience. But most often, when you see a system that doesn't look too good, right, it's due to really bad managers. So I'll give you an example. I was a student at the 3rd year at the university, and I had 3 months of actual professional experience in writing software. And a company hired me, the biggest company in the city hired me and gave me a task to design an enterprise resource planning system that would be built, that would take like 3 years to build and then to be deployed by a lot of people. You don't do this kind of thing with person who's on the 3rd year at the university, right? And has got no experience in designing system whatsoever. And that's exactly what they did, right? So I built that system, or actually I designed that system, and it looked something like this. It was really, really bad, right? But what did you expect? Like a student at the 3rd year at the university? How could that happen? And it turns out that's due to the internal problems and politics of the company. So, and that's what happens a lot. So for many years, I thought that the reason why I did that system so bad, because I made like almost all possible mistakes, right? The reason was that I had really bad education. Maybe my university was really shitty, and it was. So I read the wrong books, or I didn't understand them, something like that, right? And then I started years later, like 10 years or later, I started teaching people architecture. And it turns out, no, they make the same mistakes. So basically the education is on the same level everywhere. And I'm talking the whole Europe, for example, even with Africa, right? And Asia. So that doesn't look too good. And when I look at all of this, and now I have those students, those young people coming to my workshops and basically trying to design their systems and failing the same way I did, I find the same mistakes. So I decided to give you that talk that would be like a concentrated version of a long workshop, right? Okay, so first, all the things that I didn't understand back then, right? 18 years ago when I started doing these kind of things. First of all, there's no such thing as a bad or good architecture. It's only about architecture, whether it's optimized for what it's supposed to do. So whenever you are building a system, you have to decide what you want to optimize for. And you cannot choose everything because, well, the system optimized for everything is a system optimized for nothing, right? So you choose some quality attributes or non-functional attributes, or basically something that you want to optimize for. And you have to choose like the maximum of 3. And then you design that system, right? So what do actually people choose when they say, we are building a new system? And it turns out most developers say things like performance, or I want my system to be scalable and be able to, handle the whole traffic of the world, or anything like that. But when you think about it, and when you look at the numbers that they want to have, Well, we got 5 gigahertz of computers right here, right? So basically to do something, to make the system slow, you have to do something really stupid. And that's actually what we do. We block on the database. We basically do queries that do not hit the indexes and stuff like this, right? Think about it. This is a CPU from 1975 running Doom and powered by potatoes, right? So if we can do this kind of stuff, then why are our servers basically slow and our systems on the server, right? Of course, this Doom actually looks more like a Wolfenstein, but basically you can look it up. There's a video on this, and it really works on the CPU from 1975, including the batteries made from potatoes. So really, we have to do something really bad to make it. So instead of thinking about this, what I think you should consider is whether you would like to optimize, not for performance, just don't do stupid shit and it will work, right? But instead to think about optimizing for stuff like being able to maintain this with a small amount of people, or basically not creating a lot of work in maintenance. That's an important quality attribute for the system that you're designing, right? Because you have limited number of people. The same thing with extensibility, which is how fast it will be to add new features, right? Because there are architectures where it's really, really difficult, right? Like we are looking at one system and we are actually designing and building new features. And we found out that going to microservices would take us would get us 6 times faster to production than actually implementing the same stuff on in the monolithic application. So these are the important things. And if you are a startup, then you have to also consider this, that, well, if you are a startup, you don't have a good market position yet. So that means you are going to switch your goals and basically build a different product at the end of the day, or after 3 months or 6 months on the market, right? So if you think about the MongoDB, for example, corporation, that wasn't a MongoDB corporation. They built something completely different. It just didn't work, or didn't sell. It worked, but it didn't sell. So they changed that to something completely different. So when you're in a startup, that's what you have to optimize your system for, being able to switch, to do the pivot, to switch the goal pretty fast. Now, having said that, we have 3 different types of systems these days that are quite popular, or the most popular ones. These are like architecture flavors, because you can mix them basically, right? So you have to learn them to be able to decide and to be able to mix them in a conscious way. The first one is a modular monolith, right? Which is a single app with several modules. Then there is a distributed synchronous system and event-based microservice-based system. So basically, a distributed synchronous system is a typical microservices with REST, and event-based, you got the microservices with Kafka or any kind of an event bus or queue. Okay, so everybody talks about the good things about those systems. How about the bad things? You have to consider those as well. So I'm going to talk about the problems with those types of systems. Let's have a look at them. First of all, if you have a big modular monolithic system, then the main problem is actually that every single deployment that you're going to have is a big risk, right? Because you got 200 people working on this, and you are never sure what's going on into the production. And then even if you deploy the production and it works right now, if you have a single memory leak, that will kill the whole application later on. That's the problem with modular monoliths, right? So if your business does not allow for a risky deployment, you can't do modular monoliths. You can't do monoliths at all. You have to go into the distributed system, right? Now, the next thing is, if you got developers, and there's this thing called broken window effect, where if you see a piece of code which looks really shitty, everybody lowers their expectations for the rest of the code to the same level. And then what you have is people are working with worse and worse code base, basically, right? Because nobody cares. People are like, okay, I don't care about this code base if it already looks bad. And it takes a lot of self-discipline to actually get out of this. Then the next problem is that it's very easy to break the architecture when you have all the pieces inside your IDE, basically. That's the typical situation with modular monolith, right? So what you can protect against that is, how you can protect against that is basically with communicating. The job of the architect is actually education a lot, right? And then things like, for example, ArcUnit, which will protect the rules or the decisions that you've made or in your monolithic system. So I definitely recommend that. And then we have a limited technology evolution. Basically, there's only so many technologies you can use in a modular monolithic system. And that is a problem, actually, because after 3 years, most of the best developers will actually leave. They would like to change their job because they want something new and shiny. They already know their stuff. And these are the most important people for the system, right? So microservices, when they are heterogeneous, it doesn't have, that kind of system doesn't have that problem. So this is the problem with the modular monolithic system. And then people don't even know what a module is. So how can you build a modular monolithic system when you don't know what a module is, right? So the problem with this, I think Neil Ford actually in his previous book writes about, a whole chapter about modules. And he starts with saying, nobody gives a definition of a module because everybody is afraid to do so. Because when you're writing a book, you have to be correct. Otherwise, the book is incorrect. So basically, it's a piece of shit nobody wants to buy, right? Now, the problem is he doesn't give the definition of a module himself, I think, due to the same reasons. He gives a good estimations or basically the ways to estimate how good the module is, but not a definition. So I don't have to be correct. I just have to be helpful because I'm not a writer. I'm not writing books, right? So everything I tell you can be completely wrong. As long as it's helpful, it's okay. So I'm going to give you my definition of a module. I think that works for me. And that's this. First of all, a module is responsible for a single thing. And that thing is a process. So we have a single responsibility, right? And I'll talk more about that later on, because that's the main problem people make, or main error people make, right? Then a module is a vertical slice. It's got all the layers, access to DB, access to the domain logic, and also the UI, sometimes even the HTML or whatever else you have. If you have a single page application, that's the REST endpoints, right? It's all inside the module. And then the module has got API, and you have to understand where that API is right away, and you know who the module cooperates with. So basically, modules depend on each other. You may build a system where they do not depend on each other because they don't know about this, because they work based on events, on some kind of an event bus, but that's your decision. It doesn't make it makes it much easier, to be honest, to reason about the modules. And then the second most important thing, I think, is that modules have their own databases. Basically, you cannot do any single insert, update, select, inner join, any kind of a join, anything, okay, between tables of different modules. And that's very difficult to do for beginners. And that's the most important part, because what you really need is encapsulation. When you have an encapsulation, then what you have is that a module depends on all the APIs or APIs of all the modules, and everything else is hidden and inaccessible, right? If you use domain-driven design, then a module belongs to a single bounded context. You will never find several bounded contexts in a single module. However, a single bounded context may be built by several modules. It's okay, right? And a module defined this way is a candidate for microservice, right? And I got some examples of how to actually implement this in pure Java, but let's move on because we have some problems to solve. So when you have this kind of modules, then the first question you have is actually how small or how large those modules should be. And consider this. Think about, you got the requirement. Let's say you got a microservice or let's say another module called cost calculator. That will take all the costs for a day for a given user. And then your job and the task at hand is to actually send an invoice at the end of the day to the user through email, and that's it. And most people will say, okay, that's a job for a single module, and they will create this module, right? And that module is way too large. So how can we think about it? How big should it be? And what are the reasons, or basically how can we split it up, and when we should stop, basically, right? So think in these terms. What is the algorithm that we are going to implement in this invoice creator, or basically create the module that creates that invoice, right? And if you think about it, the algorithm goes like this. First, you have to actually create the invoice itself. So you have to understand and learn about stuff like, for example, taxes and things about what's the definition of the invoice, right? What kind of codes are there on the invoice? How do you choose them? Basically, what do you put on the invoice? That's a lot of learning, right? You should read a lot of documentation for that. Then there's the next problem. We need to create a PDF file, for example. So if you think about it, the PDF is a simple thing. However, it takes a lot of time because now you have to learn the API of that library that you chose to actually implement this. And then it takes a lot of time because it's complex, or the problem is easy, the implementation is hard. That's usually how those libraries work, right? So, and that's a completely different area of knowledge than the creating of the invoice. You had to learn the taxes for the first one, and now you have to learn a library for PDF creation. And then you have to send it through the email, right? So you will basically choose something. Let's say we'll choose Apache Camel, for example, or Spring integration, or any kind of a library, or maybe you will implement SMTP yourself, probably not. Basically, you will have another area of knowledge that you have to learn to be able to implement this. So what we have is we have 3 different areas of knowledge. And think about it this way. You want to optimize so that for your cognitive load. So basically make it as small as possible so you don't have to put all the knowledge into your head when you're implementing something or debugging something. And that's how big your modules should be. So basically what I would suggest is to split those modules down to the situation where if you split it any further, you won't be able to give it to 2 different people that would have to learn different areas of knowledge. And even if you're a single person, that will help you if you split those modules like this. Because what will happen is if you have an error and you have to go back after a month to the PDF generator, you only have to think in terms of the documentation for the library, not the documentation for the taxes themselves or the invoicing, right? So make them smaller, but do not split them if you have to have the same areas of knowledge in your brain when you implement 2 different modules, okay? Now, that creates a lot of modules, and that's okay. We already know, and that's a Unix philosophy, that this scales and actually works fine. It's easier to implement, right? So this is how small they should be. And we are not going to talk, even if you don't have the definition of a module, or you basically, nobody thinks about it, nobody defines this, and basically there are no rules. What you get at the end of the day is non-modular monolith, which we know is very difficult to maintain. So basically it's a no-go. Then we have distributed synchronous systems, and these are the typical microservices using REST or any kind of a synchronous protocol, right? So, and I'm talking only about the real ones, the ones where you have independent deployments. If you have dependent deployment, or basically you're synchronizing your deployments, that's another type of a system. That's a distributed monolith. We don't do that. That's got no benefits and basically all the problems of all the monolithic and microservices, okay? So what are the problems with this kind of REST-based microservices? Well, first of all, you have to think in terms of eventual consistency, because you cannot have transactions anymore between those systems, right? So you have to learn that. It's not very difficult, to be honest, but you have to learn how to provide eventual consistency and how to deal with this, because whenever you have 2 different machines, then you have a speed of light that will block you from having the same state on both of them at the same time. And we know from 2011 at least, where there was a white paper about it from Amazon, actually, Pat Hunt, that we don't do distributed transactions in distributed systems for performance reasons. Then you have to understand that you need DevOps. So basically developers operating their systems in production. And if you have a culture in your company, when developers actually write the code, somebody else keeps it alive on production, you can do it with microservices. The level of complexity will rise so much in terms of operations, it won't be possible anymore. So you have to change the culture of the company, right? Then you need a team for tooling. And what I mean by that is there'll be a lot of problems which are shared between different teams. That will be technical problems usually, okay? So sooner or later, you will find out that you need that single team for this kind of tools, or maybe another one, or maybe even provide some software as a service for all the other teams, right? And if you cannot afford for this, you cannot go with the microservices. So basically, if you got only a single team, maybe that's not a good way to go, right? Then you have communication inefficiency, which is overhead latency that you have to depend on. So you have to build read models, and we'll talk about this. And you got the complexity there, which means that you have to implement retries, fallbacks, circuit breakers. And again, you have to learn all of this so your system is resilient. Otherwise, it will break in all those places that in other way, the JVM or the virtual machine would protect you against, right? Now, having said that, you will only learn that your system sucks and it's got problems if you implement observability first. So basically, if you design the system to be able to say what's going on inside of it, and you have to be very careful about this, right? If the system, if your metrics and basically your dashboards lie to you, you won't notice the problem. And that's a difficult, or maybe not difficult, but it's actually, it requires a lot of thinking, okay? And then if it's not a reactive system, then you will have suboptimal CPU usage. I see that, and actually there's a lot of large systems, microservice-based systems, where the CPU used for like, we are using 10% or 20% of the CPU, and the system is slow. How is it possible? Well, when you're having microservices and people are not writing reactive code, what they do is they have thread pools. You got a thread pool for Tomcat, you got a thread pool for the database driver, for Hikari, or whatever else you're using, right? And in a single monolithic system, people are used, there's at least one person that actually can optimize those things, does the stress testing, and basically set up those thread pools. When you have microservices and you have 5 people working on a single microservice, there's a big chance nobody can do that, or basically has got no experience with this. So what you end up with is you're ending up paying for a lot of machines that you're not really using, right? And on the other hand, you can go to the reactive way, but it's more difficult. I know I teach the reactive programming, right? So, and then the last thing, you cannot do end-to-end testing anymore. And the reason for this is because the deployments are independent. Even if you have only 3 teams, you will not be able to create a testing environment that will prove that the software will work in production, because it takes too long, basically, to provide all the possible combinations of those services as they are deployed when there is no synchronization in it, okay? All right, so then we have event-driven distributed systems, and they have their own problems. First of all, you got to have somebody doing a PhD on the message bus, because if you want to use Apache Kafka, I'm very sorry, but that's not a simple system. You have to learn this, right? Now, if you think that, well, we have to keep this alive, so maybe we'll buy a closed source system, right? We're going to use something that the cloud provider provides, right? That's great. However, now you have to have somebody doing a PhD on that system without the look into the internals of that system. And also you got the marketing people lying a lot. So basically you can't trust them, right? So you have to have somebody specializing on this. And if you can afford it, sorry, you cannot go into the distributed event-driven system. Then people create a lot of chaos because they do not understand that there are public events that go between different teams. That's a different type of event than the event that goes inside a single team, where you can change. Basically, you don't have to provide this kind of the same kind of contracts as with other teams, because you control every single producer and every single consumer of the messages, right? And there are even private events that only go for a single microservice, because we can use even the distributed transaction log, the persistent distributed transaction log, as a persistence layer even, right? And there's another problem that people do not understand, that event-driven and event sourcing and event storming are talking about different kinds of events. And then design the systems saying, okay, this is the same event in all those approaches, right? And it's completely incorrect. Think about it this way. In event-driven systems, the events are what you communicate. So basically, this is communication pattern between different microservices. It doesn't imply that you have to have anything else. Now, event sourcing talks about how you persist the stuff that you have. So basically, what happened in your system from the perspective of what you should remember in your system, right? That means that you most likely are not going to publish those events as the communication pattern, because in this case, you would have to have the same contracts for the communication pattern as the persistence layer. And that's a really bad thing to do. It's like taking your entities, not converting them to DTO, and just sending them over to other microservices. And then you have event storming. And event storming provides you with a lot of business events. That doesn't mean that you have to have those business events converted into event-driven events or event sourcing events. That's a business, that's the analysis pattern. So basically, that's something completely different. It might be that they are the same thing for sometimes, but most likely they are not, okay? And people don't think about it. They see the event and that's all they see. So when you have that, the next thing I wish I knew was that actually all the microservices and modules communicate only in 3 different ways. That's the 3 possibilities there. The first one is a query. So basically I can ask you for something, find available cars. That's a question, that's synchronous by nature. Then there is a command when I express an intention. So basically do something for me, right? And that could be synchronous, could be asynchronous, depending whether I accept that you can say no, or whether I say, this is the command, you have to do it, that's it. The method type is void. And there are the events. And events are just stating a fact. So that's this is asynchronous, and that's past tense, usually something that already happened, right? Now, and it doesn't really matter whether you have REST, whether you have, whether these are calls inside your JVM. So basically, these are just method calls. These are the patterns for communication between modules and microservices. So what are the problems with them, right? Take a look at this. If you have, let's say we have 3 different modules: car rental, which knows which car are rented or not. We got locator, which knows where those cars are at the moment. So, and basically you're building another module, which is kind finder, which will be responsible for searching for those cars. Now, the natural way for a lot of people is to use the query, because this is like a simple one, right? So people design something like this. They get available cars from car rental, they get the locations from locator, and they try to search on that data. But what that means is that you have a very, very bad SQL in there, because, well, you're gonna get 500 cars from car rental, and now you are going to make a query with 500 different IDs in the locator. That's like 501 queries, really. So basically, that's inefficient. So what you have to do is something completely different. You cannot do any kind of joins, because if you could, that would be simple, but you cannot do any kind of joins because of the definition of a module, right? And then these are microservices, it's even worse, because in microservices, the optimal number of external calls, let's say these are the REST calls, would be 0. You cannot have any kind of external calls if you want to go really, really fast and provide an answer to the user, right? So how should we actually do it? The queries are very limited, turns out, right? So instead of this, you can use events, and you can switch into the read model based on events. So for example, in this case, we would send events from car renter, a car locator. We would store that information inside the database of car finder. That would be our read model, and it will be optimized for the queries that you want to run. This is the same pattern that you see with the CQRS, command query responsibility segregation, right? Prepare your read models, and they are going to be much easier for you and basically much more performant, right? So, but now we're switching from queries to events. And then there's another problem with comments as well. If you're saying that you want to send a comment from one module to another, then what you have is this kind of a situation where you have to understand what's going on inside the other module, and you have to understand when the process is going to start, right? Now, if you have just one single team, that's okay, that's fine, it works. But if those modules are built by different teams, what happens is sooner or later, the car rental team will not have the same knowledge that the cost calculator team has. There'll be changes, and those changes will now have to go to both of those teams. Otherwise, the car rental will call the calculate cost on the wrong time. Or maybe it shouldn't even call that, because we changed the algorithms, and now we are calculating the cost at a different point in time or in a completely different way. So the problem with comments is if you have several teams, then there is a chance. These are very difficult to maintain compared to events, because what would happen is if you had an event there, car rental will say something like car was rented, then you're only stating the fact that is created by the changes in that single microservice or in that single module. And that's always true. If cost calculator is not interested in that process anymore, or basically in that event, okay, because the process has changed, they can stop listening to that event. That's it. So events are much safer from my perspective in the long term, because they allow for local reasoning when you only reason about the things that happen in your system. Okay. Now, that being said, every single presentation or talk I saw about event-driven architecture and events ignores the problem of a baseline. Basically, we assume that whenever you send an event, especially when that event is a persistent, so basically you have like a Kafka or anything that can persist your events for like forever, then okay, the event is already there, right? There's no need to send it again, for example, and that's it. However, that ignores the problem that we, the developers, actually make a lot of errors. So when we make those errors, what will happen is you will have to say, okay, my car rental didn't send you all the events that it was supposed to, because I had this bug here, right? Or maybe we did send those events, but we calculated something there. So basically the data you have in those events are incorrect, right? Now what you have to do, you have to send all the events again from car rental if the problem is on the producer side, because even if they are persisted, the persisted events are incorrect on the message bus. Now, if the car rental doesn't have a bug, but the cost calculator has a bug, then what it can do, if you have a persistent event bus, or basically persistent transaction, distributed persistent transaction log, you can read from the beginning of that queue, basically, or that topic, right? And process all of them again and recalculate everything. However, it's not that simple when you have a database and your system is idempotent, right? Which is what you have to do anyway. So in that case, are you going to throw out delete basically the whole database first? Because otherwise those events are going to get ignored even when you try to read them again, right? So this kind of things are the problems that you are going to have to be prepared for whenever you're using events. But that's not everything, right? The next biggest problem is actually that people tend to think in terms of data ownership. That's a term from like 30 years ago, right? Which microservice or which, back in those days, which application or service actually provides the data or controls the data, right? If you build a system and build your module or a microservice based on nouns, like here, car module, then what you will try to have is you will have a lot of different methods operating with that noun, right? And that's completely wrong, because as you see here, this grows and it becomes very cumbersome. You cannot actually maintain this anymore, right? Too many responsibilities are going in there. So what you should do instead is think not about data ownership, but think about single point of truth, which means that you're going to have microservices or modules per process, basically, right? So now you have the same situation, but we have a car rental module and car return module, and then those modules can communicate with each other. And the rule is there is only a single place in your system that can state an event, basically, right? Tell the truth. It's a single point of truth. For example, for the information car was rented. Now that's very important, because when you have this, you can have basically control. You can basically provide invariants. So basically, you can control what happens in a single place. If you have several modules or microservices stating the same fact, who do you trust when they disagree, right? However, when things happen and you already have those events, it's safe to duplicate them. Nobody owns the events. Those events have already happened, and you can do whatever you want with them, right? So there's no data ownership. It's a single point of truth instead. So if you look at this, the single point of truth allows you to ensure invariance by providing you with a situation when you have a database and you can lock on that database. And no matter how many instances you have, the data will be fine, right? Even if you don't have a database like with a lock there are still ways to provide this, because you can partition the data, send it over to different instances, do like the things that frameworks with actors and agents do, or basically with a pure Kafka that will work as well, as long as you have each single instance subscribed to that partition, right? So it's important for us to have this single point of truth, but don't think about data ownership, okay? Now, the next problem is we design the system, and quite often what we do is we do orchestrations, and orchestrations are fine inside monolithic systems that are built by a single team. When you go when you build a system with many teams, you cannot do it anymore. Think about it this way. If I had a car rental module or a microservice, because it works both the same ways, right? And I had different teams for cost calculator, invoice creator, park committer, then what would happen if that single car rental module or microservice would send those commands, basically do something for me, now do this, now do that, and control the whole process, which is called orchestration, right? Then what happens is that if these are separate teams, again, the car rental team has got to understand all the processes around it, right? All the processes of different modules, and what should happen when, for example, something fails. How do we behave at this point? And when you have several teams, this will be not true after half a year. And basically, the knowledge of those things will go different directions. So basically, you will think that, okay, I'm in the car rental team and I control all of this, but that's not true anymore. So a much safer way to do it is actually to do choreography. So basically state your facts and allow other teams to decide what they want to do with them and give them autonomy to do so. Now, the problem with this approach is you don't have a central point where you control the whole process. So like, let's introduce Saga, right? Now, Saga, again, is the same situation. You're introducing orchestration, and orchestration doesn't work after half a year because you have different knowledge there. So basically, that's the problem. So what will happen is that you have to go with the choreography if you want to maintain the system and keep it easy to maintain. And it's going to be much easier to do so. However, to be able to see where the process is, or basically what's going on between all those modules or microservices, you will have to create another module on another microservice that will be fed through all those events, and we will try to actually make help you do reasoning about it, right? So tell you about, you know, where is my car, dude? Stuff like this, and then what's happening with it. So that's the next problem. There's another one. This is about different quality requirements. A lot of people created the single application while they have different users with different requirements. And we are talking about non-functional requirements. And this is an example from last year when in Poland, there was a system for registration of the patients for, you know, COVID vaccination, right? And there were nurses that were actually injecting those vaccines into the arms of the people using the same system, and they had to use that system to check the verified data for the user and basically enter some data there, and that's it. And that looked like a single system, right? Now, what happened is that there are different quality requirements. So the nurses, you have a fixed the number of requests per second because there are only so many of them, actually not enough of them, but they require a very high SLA because people are standing there in the queue and basically we have to handle them. On the other hand, you have patients. People who would like to register that you can provide very low SLA for that, because if I cannot do it today, I will do it tomorrow, right? However, the number of requests per second can go through the roof. Why? Because after they allowed for the registration for people born after 1981, which is, by the way, the year I was born. What we did, we actually created a distributed denial of service attack on that system, because like this, you know, people like me, they know how to code. So basically, yeah, some people wrote the scripts there, right? And so the whole system went down. The problem was that those nurses couldn't work anymore, right? So what happens with this? Well, you have to learn that whenever you have different requirements, quality requirements, it's safer and easier, much easier to build actually several systems and basically build one application for the registration that will inform the patient injector, or whatever you call that system, that the nurses work on. If you split it into two different applications, then the problem is completely solved, because if I kill that system or I kill the patient registrator, that doesn't impact the other one when I have to provide a high SLA. And that's a very important thing to consider, right? Now, think about it this way. If you have a monolithic application, then you only have one SLA due to, for example, a memory leak killing the whole system, right? But when you have distributed system, that's not true anymore. Different microservices can die and you will be still okay. So how can we think about it? You have to think about the SLA per process. So basically now you have to split your system into different applications so that you minimize a failure impact, right? So it doesn't hit everyone. And you can think about it, people usually think about, you know, providing high SLA by duplicating the system, or basically I will have several instances, not all of them will die, right? The aviation industry actually has got a different approach. They say, now we don't want to have too many engines on the airplanes, because having less engines is actually easier to keep them working correctly, right? Because you have to service them. And the same thing happens in microservices, but not with the number of the instances, but with the number of microservices themselves. If you have a single microservice, which is responsible for providing, which basically has to provide a high SLA, but it doesn't have to provide any other features, and it stays there, nobody touches this, right? Then sooner or later it will be stable, because even if it had any problems, we will solve those problems. On the other hand, if you have a microservice that has got a lot of changes and you have to provide a high SLA, guess who introduces bugs to the system? We do, developers, right? So a lot of changes means a lot of bugs means you're not going to provide high SLA. So you have to split those systems and think in terms of different quality attributes. And there are actually abstracts and white papers explaining how to do so, and basically the reasoning about that. So my recommendation here is very simple. Always, whenever you have a process that you have to provide high SLA, keep it separate and try to do it so in another application so that in which you will have a low change frequency, right? Because if you have something where you have to provide high change frequency, so basically you change the code a lot and you have to provide a high SLA, that won't work. It will be very difficult to do and it will be very stressful, and that's your health. It's not worth it, okay? Now, then you have the eventual consistency. And all I need to say is that learn the transactional outbox pattern, for example, or learn how Kafka works, and you will be okay with that. It's like people are afraid of it. Don't be. It's easy, right? You just have to learn those two things, and it will be okay. So don't try to avoid it. Try to embrace it, right? And the last thing is that back in the days, I said that I had bad education, and that's true. Maybe there were good books, but I couldn't find them. So what are the books I would recommend right now if you're new to the software architecture and you're trying to learn all of this, right? Now, here are some basics ones. Software Architecture for Developers by Simon Brown and The Fundamentals of Software Architecture and Engineering Approach. These are two very good basic books for this. If you're going or want to create event-driven systems, then I would suggest Designing Event-Driven Systems by Ben Stopford. If you want to learn reactive systems, not reactive programming, but reactive systems, there is a book called Reactive Design Patterns for Roland Kuhn. And then if you want to understand why your company has got so many problems on the organizational side, and the world looks so bad for you when you're going to distributed systems, read team topologies when you will learn how to set up those teams, right? And of course, Domain-Driven Design is also a book that you should read because, well, that was actually available back in then. That was the only book from those available back in those days, but it's important. Now, there's one more book actually, which came out actually this month. So I got it it came out on Monday, Software Architecture for the Hard Parts. And that's again by Neil Ford, Mark Richards, and two more people. I don't know if I can recommend this, but the title is very good. Ask me in 2 weeks and I'll be able to tell you that because it just came out, so I can read this. So good luck. This is the link to the talk, and actually I will paste this to the chat so that you can actually take a look at this. And now I think it's time for questions, correct? Let's have a look.
I'm on as well. Yeah, there were some questions. I think one of the most popular ones, well, you already mentioned some things, some books and some links, but basically people are interested in knowing about reactive systems. Yeah. And maybe you can recommend your own courses. I don't know. It's time for advertisement. Yeah.
So I'm from because I'm the mainstream guy. I don't use technologies which are new and shiny too much, to be honest. I actually teach reactive programming, but reactive programming is just one of the solutions, and it's actually not a solution to design the system, the reactive system, but only to implement a microservice in a reactive way. So that will help you a lot, but that's not the book that I've sent, right? The last book that I mentioned. Oh, you mean the new one? Software Architecture, the Hard Parts. Basically, yeah, Software Architecture, the Hard Parts. So in terms of designing the reactive systems, that book that I've suggested, which is let me check actually, because I don't remember the name myself. That's the Reactive Design Patterns. That's a very good book about actually designing this. And when you learn that, you will understand how they build the systems like Akka, for example, right? And why they did so.
Mm-hmm. There was another question about end-to-end testing.
Yeah.
What would be the way to implement that? And is like the feature flagging the only way to do that in the right way? Or, well, just tell us your opinion.
No. Actually, drop if you're going, because end-to-end testing is great when you do monolithic applications. If you go into the distributed systems, just drop it. Just drop it. What you have to have instead, you have to have first of all, learn test-driven, behavior-driven development so that you have every single microservice tested well inside of like in its own container, basically, right? And then the next thing that will break is communication with other microservices. And for that, what you should do is consumer-driven contracts. And there are two libraries there. For Spring guys, there is the Spring Cloud contract. And for everyone else, there is a pact, which is very popular. There's actually a lot more libraries than that, but pact is very, very popular, right? And learn how to use that pact. That will save you a lot of problems. However, it will still not save you from everything. And that's why you have to do monitoring on production. And people are scared shitless when they hear that, especially when we are talking about the bank and we are designing the banking systems. And when they say, what? We are going to test whether the system works on production, right? That's not possible. And then I come over to them and say, guys, you have 100 microservices which are deployed independently. How are you going to synchronize this? And basically, you're going to lose all the benefits of the microservices unless you understand that with microservices, what happens is the impact of a single failure is much smaller. And you have to think about the SLA not for the whole system, but for a several single process. And now you can actually create those very high SLAs by monitoring the production, learning how to implement those microservices, how they communicate, and basically providing those high SLAs only for the crucial parts, for the few microservices where you put your best people in there, right? That are crucial for everything else. And all the other microservices are like, you know, if it breaks, it breaks. I'm going to fix it tomorrow. Nobody's going to notice that.
There was also a question about the size. If you have too many mini microservices around there, doesn't it create a maintenance problem?
Yeah, so a lot of people are afraid about microservices because I never heard about anybody afraid about too many modules, right? That's good, actually. So, but with microservices, every single company that I joined, basically, or tried to help, they were like, oh no, we don't want to have nano services. We are afraid. Well, let's start with 5 systems, right? And let's start from there. And my answer to this question is, I have never seen actually a distributed system implemented and working in production, which would have 2 small microservices. Now, you could have something wrong, which is you would have empty microservices, something that does only a proxying, and that's it. That makes no sense. There is no responsibility for it. But I don't see a lot of people doing nano services. What I see instead is all of those people, or a lot of people, afraid and trying to push too much into a single microservice. And from my perspective, when you go into the microservices, as long as you have the platform for it, so basically you're going to Azure and you're basically using Kubernetes and all that stuff, developers usually try to think in terms of, you know, I can count only to 3. 0, 1, and then the infinite. That's it. So if I have more than 1, that means I have infinite, and I have to learn how to deal with that. So it's possible. It's okay. But I don't see that problem of too many microservices in terms of they are too small. I see the opposite, usually.
Yeah. And what do you think about serverless?
The what?
Serverless.
Serverless. Okay.
Lambda functions as a service.
That in a theory can go too small. Okay. So my feedback for the serverless is I did that 20 years ago in PHP because that was exactly serverless, right? You were just writing your scripts and pushing into production, and it worked, right? So basically, coming from that experience, I would say it's a perfect solution to a specific kind of problems, right? Because what I see with serverless is actually, first of all, it's going to cost you much more, right? And I'm talking about the operations part where things are operating in production and generating cost for you, right? Now, it's going to have usually what it has much higher time to production. So basically, it's easier to deploy, right? It's easier to build and deploy it faster because you don't have to think about anything else. However, because it's easier and faster, people who do this don't think too much about what they do. And so they don't create tests. They're not testing anything because who cares? I'm just deploying this to production. Let's see what's happening in production. And that works. However, later on, the maintenance of such a system can grow exponentially. And basically, you have to understand that you will have lower performance, higher cost, and a large problem with the maintenance, right? There are ways to avoid that. There are ways to where you have to introduce proper engineering techniques for those serverless stuff. But when things are easy, a lot of people are not giving a shit and basically are saying like, yeah, this is easy, I'm going to do this, and I don't have to read anything about this, and I don't have to care. And after half a year, you got a problem on production.
So what's your platform where you're deploying Microservices?
Yeah, so I'm using Kubernetes on Azure. That's the system I've been working for the last 3.5-4 years, right? Before that, I was working for a company with Mesos, because Kubernetes back in the day, believe it or not, was not the only platform that you could deploy. So we get Mesos and Marathon. But when you are working in a very large organization, like the one I worked for was 700 microservices, then you don't really see that too much, because all the tools are already provided and things are as a service, provided as a service. So the goal when you have 1,000 developers or 700 developers, the goal here is to provide seamless integration for your teams and tools that they don't have to think too much about. And it's beautiful when it works. It's beautiful because you can really focus. Like, I want a new microservice. You know how long it takes for me to get a new microservice base and with all the pipelines to get into production? 4.5 seconds. I counted that. Okay, because I got the script that creates this kind of repositories, pipelines, everything connects to Kafka and to the database. That's it. That's perfect. Now, if you know that you can have a new microservice in 4.5 seconds, you're not afraid of creating a lot of microservices there, right? Now, you should be afraid about, you have to understand what observability is, because otherwise you will not know whether it works. You have to understand that this creates maintenance unless you're not working with that microservice anymore, because things are stable in production. So there are considerations there, but way too many for this talk.